So welcome everyone to the 2021 Darwin Day celebration of science that is put on by the University of Alabama at Birmingham Department of Biology. My name is Stacy Kruger Hadfield, and on behalf of the Darwin Day Committee, which includes myself, Dr. Peggy Biga, and Dr. Jeff Morris, we welcome you today to the universal celebration that we hold worldwide and across the country on Charles Darwin's birthday. He was born 212 years ago today. And on this day, we commemorate his contributions to science and the importance of communicating accurate science to all audiences. The Department of Biology has hosted Darwin Day events for the last 9 years, and we have hosted a variety of speakers that have talked to the wider Birmingham community about a wide variety of topics. In 2013, we hosted Jim Lacefield, a local geologist. In 2014, we had the pleasure of hosting our distinguished professor and chair of the Department of Biology, Dr. Stephen Austed. In 2015, we had Carl Zimmer and Dr. Franz de Waal. In 2016, Josh Rosenau and Dr. Elisabetta Palagi. In 2017, we had Joe Palka from NPR. In 2018, Genevieve von Petzinger. In 2019, Dr. Beatrice Hahn returned to her old stomping grounds around UAB to talk to us about HIV. And then in 2020, we had Dr. Brianna Pobiner, who also has an Alabama connection. She's working with colleagues in the School of Education to figure out ways to better communicate evolution in Alabama schools. But this year, as we all know, because probably many of us are watching this event from the comfort of our own homes and have been doing so for almost 12 months, we had to do things a little bit differently because we couldn't have our typical face-to-face event on campus. And so the committee got together and tried to figure out something that would be interesting to the wider Birmingham community and also people that we might reach further afield due to the virtual nature of this event. And we decided that it would be an interesting topic to understand how UAB has responded to the COVID-19 pandemic. So this year we have the pleasure of hosting 3 of our UAB colleagues, Dr. Nathan Erdmann, Dr. Paul Goepfert, and Dr. Jeanne Marrazzo. Dr. Erdmann earned his MD and PhD from the University of Nebraska Medical Center while researching the mechanisms of HIV-mediated inflammation and neurotoxicity. He then joined UAB's ABIM research pathway, a physician scientist program in the internal medicine residency training program. After residency, he completed an infectious diseases fellowship at UAB. He joined the UAB faculty in 2015 and is now an assistant professor of medicine in the Division of Infectious Diseases at UAB. He has helped coordinate UAB's COVID-19 treatment strategies and trial participation, supervising the ACTT remdesivir study. His non-COVID research centers on T-cell responses in HIV. Dr. Paul Goepfert earned his MD from the Baylor College of Medicine, and he completed an internal medicine residency followed by infectious diseases fellowship at UAB. He joined the UAB faculty in 1997 and is a professor of medicine in the Division of Infectious Diseases and is the director of the Alabama Vaccine Research Clinic at UAB. As that director, he oversees clinical trials for vaccines, including the COVID-19 vaccines. His non-COVID research focuses on T-cell immunology and vaccine design, particularly on the testing of preventative HIV vaccines. And finally, Dr. Jeanne Marrazzo earned her MD from Jefferson Medical College, followed by a residency at Yale and a fellowship at the University of Washington. She joined the UAB faculty in 2016 and is a professor of medicine and the director of the Division of Infectious Diseases at UAB. She has served on Governor Kay Ivey's COVID-19 task force and leads the UAB COVID-19 response initiatives and treats COVID-19 patients. Her non-COVID research and education efforts focus on sexually transmitted infections, especially as they affect women's health. Her other research include prevention of HIV infection using biomedical interventions. So on behalf of the Department of Biology and the Darwin Day Committee, it is my pleasure to introduce Dr. Marrazzo, who will speak to us first. I would encourage any participants in this webinar who have a question to fill in the questions into the Q&A function at the bottom of the webinar. And then after Dr. Marrazzo, Dr. Goepfert, and Dr. Erdmann speak to us, we will then have a panel discussion where we will read your questions and they will answer them. So with that, Dr. Marrazzo, take it away.
Great. Thanks so much, Stacy. Sorry, I'm delighted to be here, and I'm just going to get my slideshow organized, and hopefully everybody can see that. So really excited to be here. That was an illustrious group of prior speakers that you mentioned. So I feel very humbled by that. And really delighted to share the stage with Paul and Nathan, who I think will be a real treat for you to hear. Certainly, we would not be where we are in our dealing with this pandemic without either of them and the many people in the School of Medicine who've worked so hard to do this. So what I'm going to do is just very briefly open things up by summarizing where we are today and focusing a bit on where Alabama is in particular. And then we can come back to some of these issues during the question and answer session. So this is a slide that Dr. Anthony Fauci from the NIH shared with us. And what it shows you is now a bit out of date, but it gives you a sense of what I think are kind of the major epidemiologic trends that we have seen over the past year with this pandemic due to SARS-CoV-2. You can remember back in the spring that we had a surge, and these are data from the entire United States. We had a surge that started in the middle of March and was really intense in the New York City region, in some of the West Coast, and in New Jersey, Connecticut, New England. That was followed by a sort of slow decline in cases. And in that period of time, we saw a lot of very intense lockdowns. And you can remember there was debate about what masks to use. There was a debate about whether you should even open up your mail without leaving it on the counter for 24 hours. I would say it was a period of a lot of reactivity and a lot of very quick knowledge generation. And it became very clear during that time that given the pace of antiviral development, we were almost certainly going to need to embark on a vaccine control program, which indeed we did. So what happened after that? Well, people did comply variably and heterogeneously, I would say, with the recommendations to mask up, use hand hygiene, and use social distancing, which remain the three pillars of our ability to control this pandemic, with the addition of vaccine more recently. And then things kind of changed around Memorial Day weekend. People started to gather more, socialize more, lots of activity around July 4th. And we see the spike in cases in the middle of July and August. And that was quite frightening for us. That's when we really started to experience our surge, primarily in our hospitals. We had peak numbers in our ICUs and in our hospitals across the state. And then people again got the message, right? So you're seeing a really interesting kind of pendulum swinging here, up, down, up, down. And then what happened? Things were sort of simmering along at the end of the summer, and people went back to school, especially universities, colleges, and everybody moved back inside to start socializing. And you see this dramatic spike, which started at the end of October and only in the last couple of weeks is finally letting up. And we can talk about why that is if we've got time. But what I would like to point out here is that the epidemiologic curves really reflect a lot of complex things, including the behavior of the communities who are most infected and affected by this virus. So we can come back to that if we've got some time. So where are we right now? And these are the data from yesterday. The New York Times has an excellent tracking feature. If you haven't seen that, it's as does the Washington Post, but the Times I think has been really very, very good at this. And this is where we are in the United States as of yesterday. And hopefully you can see my pointer, but starting back in March over here, these are just the number of cases reported. Again, you're seeing those two peaks and then this gigantic peak here that really peaked in the early part of January. And since that time, we have been seeing a marked decline in cases. And in fact, if you look at the 14-day change of cases reported in the United States, well, we are at over 27 million cases. We have had a sustained change over the last month, as you can see. Now, we're still seeing a lot of cases. We're seeing almost 100,000 cases a day. So it's not like we can sort of throw down the gauntlet and celebrate yet, but it is looking very positive. What is worrisome though, and we have seen this again and again, is a lag between the peak in the cases and then hospitalizations and deaths. Luckily, our hospitalizations have come down quite a bit. As you can see here, about 77,000 people hospitalized in the United States right now. That's down by about 27% 5% over the last 2 weeks. But our deaths, unfortunately, are taking longer to come down. And that's a complicated statistic that we can come back to if you would like. But basically, attributing a death to COVID infection is not as simple as it sounds. Sorry, I'm going to go back to this because I'm not quite finished. But going in the right direction, just taking some time. And if you look at it right now, about 3,300 people are still dying every day from COVID. So really, really devastating pandemic. And this is the distribution of cases, as you can see right here, pretty much less red than many talks I've given over the last 6 months. So again, moving in the right direction. And you can see Alabama not looking too bad, as we're going to talk about in a little bit. The hotter the red intensity is, the more cases you're seeing in the past week. So this is a nice map because it gives you a sense of what's happening in the past week. So a sense of incidence and recent patterns. Now, vaccine rollout continues to move slowly, but it is getting better, and we'll see those data in a second. In the United States, almost 34 million people have received at least one dose, and 10.5 million people are fully vaccinated as of yesterday, and we're delivering over 1.5 million doses a day on average. So I think that's something to celebrate, even though I think it's going to need to go faster to get us where we need to go. Now, what's going on in Alabama and what has been our response? Let me just take a quick look at these. You can see that our count of cases is, in terms of a pattern, pretty much exactly reflective of what I showed you for the United States. We've been exactly the same in terms of our reaction to, with the exception of not seeing a large peak, as I mentioned, until the summer. We were pretty lucky in delaying the intense onset of a high number of cases, but we're getting close to 500,000 cases here. And very sadly, we're almost at 9,000 people who've lost their lives in the state, which is really staggering. In fact, if you look at the incidence, mortality incidence of people who've died basically per capita, Alabama has one of the worst numbers, and we can talk about why that is in a little bit. When you look at where we're seeing disease in the state over here on the right-hand side, again, this reflects the average number of cases in the last week. It's pretty much everywhere, but definitely more cases in the Black Belt area, north of Montgomery, south of Birmingham, and that's also been a consistent pattern throughout. So I'm going to just orient you very quickly about a few things about the clinical disease that I think will set the stage for both Nathan and Paul to tell you more specifics about therapy and prevention. But I want to focus on what we've learned in the last 6 months. So we continue to recognize that most people actually don't get severely ill. We think probably between 75% and 80% of people have a pretty mild to moderate flu-like illness. That doesn't mean it's fun. A lot of people, even though they may be able to function, lose their sense of smell or their sense of taste, and that can persist for a long time. So it's not a really nice infection, even if you don't, quote unquote, get that sick. The other big challenge, of course, is that a not insubstantial minority, probably about 15% of people, have severe disease. And that is embodied by trouble breathing, trouble oxygenating your lungs. And hypoxia, in fact, is the cardinal problem with this infection as people come into the hospital. What happens is that in the beginning of this infection, as Nathan will emphasize, you've got a big viral issue. So the virus is multiplying like crazy. Your body sort of gets that under control. You stop multiplying in terms of your viral load. And then you have this cytokine storm, which is really an immunologic overreaction. And that's what's responsible for the later phase of illness, which is where steroids and other immunomodulators come in. The other big challenge with this disease is that it doesn't just affect the lungs. It affects all parts of the body, as I'll show you in the next slide. And then the other huge problem for us in Alabama is that the people who do not do well are people who have comorbidities, is what we call them, which means concomitant medical illnesses. And there are things like cardiovascular disease, diabetes, hypertension, chronic lung disease, cancer, chronic kidney disease. Obesity is a gigantic one, no pun intended, and we don't really know why that is. And we are seeing, as being seen across the globe, a disproportionate disproportionate mortality in people who are not white, particularly Black and Hispanic persons. Some of that is probably related to these comorbidities, but there is almost certainly some independent factor at play here, which we really don't understand. And then the last thing we've really come to appreciate is that most transmission, or at least half of transmission, probably occurs before people are symptomatic or in people who never really develop notable symptoms. That's why it's been so hard. And that's why it's not worth screening, for example, just using a temperature gauge, because you really can't reliably screen out people who are infected if you just rely on symptoms or signs like fever. Other things we learned, just to emphasize, remember I mentioned that in the beginning, people were very, very vigilant about packages. They were wiping things down. They were sort of using tons of hand sanitizer. I think that's still really good. But I do think that the major mode of transmission is almost certainly person to person through respiratory transmission. So whether you're talking about droplets, particles, aerosol, it's a spectrum of transmitting things through the air from people who are coughing, sneezing, talking, singing. Singing actually is a major concern because when you sing, you really breathe out a lot of viral particles. So important to know that. The other thing is that when people are most contagious, it's during this early part of their illness. After 9 days or so, most everybody is not going to be able to transmit live virus, with a few exceptions. So those are some things that I think we've learned. The other issue I just want to mention is pregnancy. It is not a good infection to get if you're pregnant. It's probably not as bad as getting influenza when you're pregnant, which can be highly morbid and mortal, but it is associated with worse outcomes in pregnancy. One good thing about infection in pregnancy is that very uncommon for the virus to be transmitted to the baby in utero or around the time of delivery, which is really good because that, of course, would complicate matters even further. So remember, the primary symptoms are very much like a flu-like illness, with the exception of a couple of things. I mentioned loss of taste and smell. Very interesting data to talk about why that is. Interesting involvement of the olfactory nerves in particular. And also a lot of involvement of the gastrointestinal tract. I would say of the people that we see in clinic in particular who have this infection, everybody loses their appetite very early, and a lot of people have significant nausea and vomiting. Diarrhea, I've seen people who've lost 10 to 12 pounds from the GI symptoms, and that's a little bit unusual for coronaviruses. So again, it's a little bit of a weird virus. The other thing is headache. Headache early on is often one of the first symptoms. The other huge thing we've learned, and I think should be of interest to pretty much everybody on this call, is that the initial manifestations of this infection are not the end, unfortunately. We don't know how often people go on to develop long-term sequelae of COVID. You may have heard this called long haul COVID, long-term COVID, long COVID. These are things where the organ systems that are affected during the acute COVID illness experience significant and sustained dysfunction. And it can range from pulmonary or lung involvement. So people have a sense of breathlessness, dyspnea, shortness of breath when they exert themselves. And sometimes it's in the absence of measurable low levels of oxygen. So it looks like they're normal, their chest x-rays are normal, but they have this sense that they just can't get enough air. We also see people who have the opposite end of the spectrum, we think, that is scarring in the lungs. So you end up with dysfunction in breathing from that perspective. We have seen cardiac problems, including cardiac failure, heart failure. We have seen neurologic problems, and we see a lot of blood pressure problems where people get low blood pressure and just don't really regulate their homeostasis very well. The problem is that the entry receptor for this virus, as most of you probably know, is the ACE2 receptor. And while that is very prominent in your nasopharyngeal airways, it's also present throughout the body, particularly in the kidneys. So lots of problems with post-COVID. And that's not even counting the neuropsychiatric effects. A lot of people are dealing with depression, anxiety. They can't get back to their full function. We've seen a lot of young people, fully functional, highly employed, who just don't feel like themselves 3 to 6 months after this infection. So here's just a visual of some of the extra pulmonary, meaning outside of the lungs, manifestations of COVID that we have seen that can last. So most of these I've mentioned, but pretty much every organ system can be involved. I'll just mention this and then I'm going to finish up and turn it over to my colleagues. You're going to hear them talk about biomedical prevention and biomedical treatment, but I do want to remind people that the behavioral prevention of COVID, namely masking up, and with the CDC guidance this week emphasizing that better masks are better, which isn't surprising, but so whether it's a double layered mask or whether it's a close fitting cloth masks, that's really going to be the most protection that you're going to get. Hand washing, and especially to prevent fomite transmission from your nose, touching your nose and then shaking someone's hand, forget it, don't do that. And then physical distancing, more than a meter ideally, which is what we have been really emphasizing. Part of the reason we're revisiting these basic fundamentals is because of the new variants, which we would talk about if we've got some time. These new variants are evolutionary mutations in the virus that we're seeing now rapidly spreading in the population. And as you'll hear, there are some concerns that they are going to perhaps escape not just treatment, but some prevention modalities. Certainly, they're more transmissible. The UK variant, B1117, probably 35 to 40% more transmissible than the virus that we started out with. So it remains critically important that people do this, even if they've been vaccinated, as you will hear in a moment. And with that, I'm going to just set the stage for a discussion about biomedical prevention and treatment. And I will just mention briefly what's going on here in Alabama with vaccine. And you're going to hear a lot more about the actual vaccine process from Dr. Goepfert. But suffice it to say that at this pace, we are not going to achieve vaccine-induced immunity in Alabama for a long time. Some of the models say probably 2 years. And at that point, who knows what variants might be circulating in our population. So we've gotten almost 1 million doses in Alabama, and we have administered just over half of those. And you can see that we actually have been doing pretty well until last week. We were administering over 100,000 doses per week. We're doing both Moderna and Pfizer vaccines, which you'll hear about pretty much in equal measure. As you can see over here, didn't do so great last week. And my understanding is because delivery of these vaccines has been held up. So we have a lot of work to do. And if you've tried to get vaccinated or get your parents or other friends or family vaccinated, you know how challenging it is. So 8.4% of people in the state have gotten a dose. 2% have received 2 doses. That's not enough when we got to do better. So with that, I'm going to stop and turn it over to, I believe Nathan is our next speaker. And thanks for listening and look forward to talking more later. I'm going to stop sharing. There you go.
Perfect. I'll see if I can get mine up. Thank you all for the invitation to present. It's an honor. And thank you, Jeanne, for a really nice segue into thinking about the overall pandemic. And then I'm going to dig into a little bit more on the therapeutic specifically. So my task, at least as I understand it, is to talk about COVID clinical trials, specifically what happened at UAB, and then how that fits into the larger treatment picture. And the way I'm going to do this is kind of revisit some of the chaos that happened early and then kind of show how the picture developed from there. So predictably, this is a new pathogen, so there was no clinically proven treatments to begin with. We had the benefit of having some preclinical research that had been focused on SARS and MERS, so we weren't kind of in an abyss to try to figure out how to proceed with this. But yet, as the pandemic rapidly evolved, we were at a loss for kind of immediate therapeutics and how best to leverage what we did or didn't have at the time. Remdesivir was identified very early on as a potential treatment because while not designed for coronaviruses or COVID-19 specifically, It had been recognized to have activity against SARS-1 and had actually been given to humans previously in a clinical trial looking at Ebola. In that study, it was given to about 500 people and didn't seem to have as much benefit as at least one of the other arms. So it didn't have any kind of future therapeutic applications at that time. And one of the things that's been remarkable about COVID-19 is how rapidly data was generated for each of these phases. So we had viral sequence that was reported as early as January, and around that same time, the first in vitro studies were being done, identifying compounds that appeared to interrupt viral replication. And again, remdesivir was one of the very early ones that did so. Based upon that kind of preliminary data, that led to the NIAID, so a branch of the NIH, rolling out the ACT platform. This is intended to be an adaptive kind of gold standard trial platform to look at therapeutics in rapid succession. So this first study that was rolled out was specifically looking at remdesivir, and it was a placebo blinded controlled study that was going to look at does remdesivir improve clinical outcomes. So a really important thing to keep in mind thinking about clinical trials at large, like usually these take not months, but years to develop, lay out, build a network, and start thinking about how this is going to be done effectively. Obviously, that was just an unacceptable option with a global pandemic. But you take what is normally a complex process, and then you mix in literally a global pandemic, and everything is just tremendously hard. So every single interaction with the staff and potential patients has to mitigate exposure, because obviously we can't compound our infection numbers by exposing our own staff. There's an issue early on, which has been largely managed, but has not happened accidentally, which is PPE consumption. So everything needs to be thoughtful. Each interaction needs to have a purpose and needs to be optimized. It is hard to kind of sit down with someone who is scared and feels miserable and have them participate in a study. It is even more so when you're wearing one of these get-ups here where they can't see you except for your little eyes behind these masks, and you're walking around in full bodysuits. It's just hard to have a full conversation. And when you're yelling over high flow and the air circulators and everything else. And then, oh, by the way, to do a study, we have to collect and process specimens. And this is by definition happening with a pathogen that we're just now kind of sorting out how best to work. So this is a whole series of complications. And then everything in the hospital kind of has to adopt and accommodate this. So start thinking about what this needs to do to be able to roll out this study. So we need to identify who has COVID. Turns out that means we have to be able to test for COVID, which didn't happen right away. If you recall, back in February, March, April, just getting tests available and reported was not something simple. For our hospital process, for me to put someone on study, we need to be able to screen those people and then be able to find them. That has to happen very quickly. We need to be able to consent them. It sounds relatively straightforward. We do this across UAB and health systems all the time, putting people on study, but are we going to do a paper consent? If we're going to do a paper consent, where do we get our pen? Where do we have the paper? How do we store that consent? How do we upload that consent to make sure that we're upholding our obligations to the study and to the patients? Collecting the samples, again, who's going to collect them? When is that going to happen? How are we going to not use more PPE? How are we not going to expose anyone more than we don't need to? Providing the study product. Again, we are now going to have to build out a rollout process, which is usually relatively intensive to deliver a study product, but has to happen on a COVID ward. Medical supervision of the study. Again, I need to be looking at these people, but I need to make sure I don't impede the clinical process. And then we need to make sure that we're not using any more PPE than necessary. All of the data that needs to be rolled out, all the systems. There's outpatient follow-up for this study as well. And all this is happening in the context of, although we didn't have a tremendous early swell, as Dr. Marrazzo mentioned, we were having this ever increasing number, which was putting more pressure on the system at large. And the other thing to keep in mind is that as we were rolling out this study, we didn't have other options. When someone came in with COVID, if they were sick, we would put them on oxygen. And then largely we would kind of wait and watch. And that is a miserable situation for everyone involved. And when we did have the option of putting someone on study, there was obviously a lot of pressure to try to be able to do so. All right, so I was going to walk through a timeline, just kind of how quickly this happened for us. So on March 4th, that was the first time that we received the protocol and started evaluating how we could implement that. On March 15th, not 2 weeks later, we had the site initiation visit. And again, this is usually something that happens over months. On 24th, we had a virtual initiation visit. So we were officially deemed to be open for enrollment on the 25th. This time, about 1/4 of the study had already been enrolled across the country and the world. And we were looking to enroll maybe up to 8 participants and 12 overall over the next 2 years. I was digging through this timeline and found this email that I had sent to Dr. Goepfert, actually saying that we have everything in place. We're going to enroll 2 participants tomorrow. We should be infusing by midday. Kind of predictably in COVID land, that did not happen. We screened all sorts of patients. We're running all over the hospital. Everyone's testing was out of date, trying to get people that actually qualified for the study. We ended up giving our first dose of drugs starting at 6 p.m. And that's a credit to all the people in these pictures, because what happened over and over again is that working as hard as you could didn't necessarily mean it was efficient. It was very typical that we were here till 8, 9, 10, 11 o'clock at night trying to wrap everyone up and taking care of our folks. By April 19th, the first phase of the study closed, which is also extraordinary. This is April 19th, 2020, when we first described the virus in January. We ended up enrolling 16 people here at UAB. By April 27th, immediately after the study had closed, the DSMB reviewed the initial data and made us unblind our own inpatients so that we could determine who may have not received treatment because there appeared to be a signal of benefit. And by May 1st, there was an emergency use authorization to use remdesivir in those that had a moderate to severe illness. This didn't really close the phase. It wasn't until November of last year that our last patient that had been enrolled on the study in April that year actually left the hospital. So there are people that have unbelievably severe illnesses, and obviously there's a high mortality that's associated with those that have more severe illness, but it can be really debilitating and profound for some. I do not want to intimidate those that don't spend lots of time looking at charts, but I wanted to go ahead and include some real data here. The blue line, those that received drug. The red, those that were receiving a blinded product but ended up being placebo. Where it separates is where you're having a difference between the 2 interventions. And as this goes up, that's the number of recoveries. So that's people that are now 29 days out from when they came on the study, and they are now deemed recovered. And you can see when this study ends is that remdesivir ends up sustaining a benefit overall, which is why we say that the study met its primary endpoint. This over here, anytime you see a line that it starts and ends on this side of the line suggests that there is a statistically significant trend in that group, that this was a real observation. When it crosses the line, the statistics can't quite power it, but you can see that there's a very consistent signal across that remdesivir helped all these different groups with those that had moderate to severe disease. And that was the finding of this study. There's another way to look at it. People that are red have died. People that are blue have recovered and have no ongoing oxygen requirement. The top line is those that were getting remdesivir. The lower line here is those that were getting placebo. This is for those that were coming in on nasal cannula. You see how these 2 bars start separating out. And all these over here are different kind of subgroup analyses and findings. So this is how this study worked, and this is why we implemented the findings. So because science isn't always straightforward and uniform, another study came out over the summer. Remember I showed you those blue and red lines? Here's these blue and red lines. And in this study, they're showing with remdesivir that they didn't separate. And so how do we kind of leverage these different data sets and recommend treatments for our patients? So this is a different type of study. And one of the challenges with COVID has been that there are the kind of the gold standard, which is a very resource and time dependent study like ACT. And then there's these other pragmatic studies where they very kind of distill down the process and identify patients that do or don't have COVID, and they put them on an arm of the study. And the Solidarity study was one of these pragmatic studies that actually enrolled all across the world. And in this study, they didn't see a difference in people that did or did not get remdesivir. So there's some differences though when you start looking at these different studies. In the Solidarity study, there was no placebo or double blinding. And again, that's not intended to be a negative over the overall study because they enrolled thousands of people in this study. But by not having placebos and blinding, that does allow some bias for who gets put on what arm, how they're managed, and it complicates the interpretation. Another change is that for the ACT studies that there had to be a positive PCR test within 72 hours of getting their first dose of drug, and there was no time defined for the Solidarity study. And then the severity of illness isn't captured in the adverse events weren't captured in the same way or at all, frankly, in the Solidarity study. And when you compare that to with what we were able to determine on the ACT platform and the consistent findings, that's kind of what led to the interpretation that when you could define these parameters that remdesivir had benefit. For us here at UAB, starting with the emergency use authorization in May, we had to develop, as is always the case with COVID, you end up with a new mandate and have to figure out how to make it work. So one of the things we did is try to figure out how to scale up providing a uniform access to remdesivir in an appropriate way. This started off with the ACT platform and then expanded access, which was run by Dr. Rana. And then we quickly scaled over to doing emergency use authorization. you can see this is what our consumption of remdesivir over the months, where we were beginning this process and we hit that peak in July that was mentioned previously, that things leveled off. And then we hit this massive peak where we had 430 individuals that were treated with remdesivir just in December alone. And the process worked only because of the tremendous input of our pharmacists, specifically Matt Brown, Seth Edwards. And where we were doing this is that every individual course was actually reviewed by me or another physician. And that's how we kind of managed to apply the drug appropriately. Last fall, FDA officially approved remdesivir as the only COVID-specific therapy to date. There's some anti-inflammatories that we use. This is the only one that's an antiviral. I wanted to briefly touch on the next kind of phase of the study. So after completing the first phase of ACT, which looked at the antiviral remdesivir, we looked at an anti-inflammatory called baricitinib. This is a drug that was already FDA approved for a type of arthritis called rheumatoid arthritis. And it shuts down some of the cytokine signaling that the immune system does when it's activated. And as mentioned, there's two phases of the COVID illness. The first is the typical viral syndrome. And then the second is this overwhelming inflammatory response that some individuals have that leads to the respiratory presentation. So this study looked at the combination of the antiviral along with either a placebo or baricitinib. And just briefly, again, you see these two lines here. The blue is those that was getting the intervention. The red is those that were receiving placebo. Interestingly, both of these are receiving remdesivir. And just in the time between phase 1 and phase 2, the overall outcomes improved somewhat as we got better and better at managing COVID-19 in the hospital setting. But even with that, we still see a difference when baricitinib was added to the remdesivir. And so this was a statistically significant finding showing that those that received baricitinib were more likely to leave the hospital sooner and had less overall complications. So this result came out shortly after another study reported that steroids also had a benefit. And that's an ongoing question of how do we best manage the inflammatory changes that are notable for COVID. Looking at these studies, again, they're different studies, and there was a really high mortality in the report that showed steroids versus the relatively low mortality in those that were on the ACT platform. Baricitinib was seen to have more effect on those that were earlier on or had less severe respiratory presentations, whereas steroids seemed to have the most benefit in those that had respiratory failure requiring mechanical ventilation. And the studies themselves were different. And these differences are what led us to conduct our current phase of the study, which is now ACT 4. What we're doing here is we're giving remdesivir with either baricitinib or dexamethasone, and both study drugs are blinded. So that study is about 1/3 of the way through right now. So these are not the only study platforms that have been going on at UAB. I've been running a committee with the help of people from across the institution to try to accurately identify COVID positive patients, screen them for potential studies, allocate them to those studies, and do so in a way that doesn't lead to our patients being pulled in multiple directions and complicating the clinical management of these patients. So far, we've specifically assigned over 800 patients that we've screened and evaluated and funneled those over to individual studies. We've had well over 150 patients that have been enrolled onto clinical trials at UAB, and that's just from the inpatient setting. That's not including vaccine trials, that's not including outpatient stuff. And the participants that have enrolled in, and one of the benefits of being at UAB is that we're able to access some of the populations that are most at risk. So we've had about 55% of our participants have been Caucasian, whereas 45% of thereabouts have been African American, which has been really important because that's one of the blind spots for a lot of these studies, is making sure we access the populations that are most at risk. Also, all happening in the background is that we're trying to enroll people to be able to better understand the natural history and the immunology of COVID. With Dr. Goepfert's help, he and I have worked on the outpatient setting where we have, in many cases, sequential samples from over 200 convalescent patients. With the work of some amazing help from our clinical team and some of our research personnel, we've enrolled over 2,000 people here from UAB inpatients and have samples with pretty valuable and difficult to obtain sets of PBMCs from over 600 individuals. We have hundreds of sets of urine, hundreds of sets of saline. And these are really going to provide the foundation for work that has already been done, but also work that's going to be done for the years to come to understand acute severe COVID, and then bridging the gap between what we understood at the beginning and now as we have these long-term syndromes and as therapeutics change. Anything that I talked about relied heavily upon lots and lots and lots of other people. I'm going to spare you all walking through this, but there's a lot of people that have put an amazing effort into all of these processes, and my thanks to every one of them for consistently coming to bat. All right, I'm going to stop sharing my screen, let Dr. Goepfert go. And again, thank you for your attention.
Thank you for the invitation to speak. It is an honor, as was mentioned by the prior speakers. I'm going to tell you about the vaccines, obviously. So I want to start with just talking about the fact that antibodies are the primary correlates of vaccine protection. This is showing different vaccines, pathogens for vaccines that are available to prevent these pathogenic illnesses. And what you can see is that the different types of antibodies are what are the correlate of protection. So if you can make a vaccine that induces these types of antibodies, you can protect against these diseases. And central to that are what are called neutralizing antibodies. So what are neutralizing antibodies? And this is just a cartoon representation of, this is an actual SARS, or I think this is a rhinovirus, but I made it look like SARS-CoV-2. And so this is a virus then that attaches, and SARS-CoV-2, as Dr. Marrazzo mentioned, uses ACE2 as the receptor, the cellular receptor. And so it binds through the spike protein of the SARS-CoV-2. It's called a receptor binding domain. And it binds ACE2, and then that gets what's called endocytosed, and then you get cell infection. If you're able to induce antibodies, which can be induced during natural infection, it can also be induced, obviously, by vaccination, now that we know. You can actually block this. So then what happens is the antibodies that are shown here in this Y-type structure bind to the surface of the SARS-CoV-2. And the antibodies that we induce are all towards the surface protein, and I'll get to that in a second, called the spike protein. And what they do then is they then do not allow the virus then to attach to its ACE2 receptor. And when they do that, then that prevents infection completely. And it essentially neutralizes the virus. And so this is the kind, we've known this for a long time. And so back a year ago, we knew that this is the kind of immune response that we want to induce in a vaccine. And so a huge number of vaccine candidates came out last year to develop and to combat the SARS-CoV-2. And these are shown all on here. You can see that it's hundreds of different types, but most of them right now are still in preclinical development. Fortunately, these the ones that are shown here with this green, Pfizer, Moderna, which is an RNA vaccine, which I'll get to in a second, Novavax and Sanofi, which are protein-based vaccines. It's the older technology. I'll talk about a little bit about that. And AstraZeneca and Janssen are a recombinant, somewhat newer technology as well, recombinant adenovirus protein vaccines, or adenovirus recombinant vaccines. And so these have all undergone or are undergoing or will undergo phase 3 studies. And I'm going to focus mainly on the RNA vaccines because obviously that's what is available now in the United States and of most interest to most people in this country. So I'm going to mainly focus on the Moderna vaccine. Pfizer sort of mirrors this. Moderna was made a huge part with a collaborative effort with the NIH, and UAB is involved with many NIH studies, and we've sort of morphed into what's called the COVID Prevention Network, and we're part of that, which is a huge multinational consortium now. So December 31st now of 2019, COVID was first reported in China, in Wuhan, China. Amazingly, 10 days after that, they sequenced this virus. Maybe they sequenced it before that, but they made it publicly available. And then 7 days after that, they created the first vaccine, which happened to be the mRNA vaccine. And it happens that mRNA vaccines are very easy to synthesize. And so you can do this very quickly. And so that's one of the reasons that I'll get to in a second why mRNA vaccines were developed so rapidly. So the NIH, in concert with Moderna, developed this vaccine. They also figured out which part exactly of COVID to target, and I'll get to that. So then March 16th, they started phase 1/2 studies. So they made enough vaccine to do studies, which are initial studies. Phase 1 is first in human studies to test safety. Phase 2 studies test safety and immunogenicity. Well, they received US government support at this time to carry on phase 3 studies. They received a lot of support to do that. And then July 27th, they started the phase 3 studies. They got more additional support when it started looking promising. The phase 1/2 studies showed that they were indeed inducing neutralizing antibody responses. So the government decided to buy a vaccine product in anticipation that it may work. And then November 16th, I think it exceeded most everybody's expectations. This vaccine, Moderna, was 94% effective in the United States in preventing infection. And Pfizer showed similar data a week before that, 95% effective. And so then in December, at the end of December, an emergency use authorization was approved by the FDA. So one of the things that a lot of people worry about is, how could you have developed this vaccine so rapidly within 1 year? And I think I'd like to just give you the, let you know that it has nothing to do with skimping on safety. It has a lot to do with being lucky and also being somewhat prepared beforehand, and then also new technology. So we knew the spike protein back with SARS-1 back in 2003 is the Achilles heel of coronaviruses. We know that if you can develop an immune response to that, you can knock out the virus, if you will. So we already knew to target that. And that sometimes takes years to figure out. We rapidly identified and sequenced the virus, as was mentioned. mRNA technology, messenger RNA technology, has been around for 15 years, but fortunately now they figured out how to preserve it somewhat to use it as a useful vaccine, and this allows for rapid development. There was some innovative design trial that happened where we combined phases 1 and 2, and then also designed phase 3 during that time when this was happening. The other thing is we had huge community buy-in. And we had rapid enrollment of over 30,000 people very quickly into these studies, at least 30,000 or more. And then sadly, as Dr. Marrazzo was discussing, we've had ongoing huge numbers of infections in this country and other countries as well, which allows you to actually determine whether a vaccine works very quickly. So how do RNA vaccines work? We knew, as I talked about, that you want to target the spike protein, which is the surface protein of the coronavirus. Scientists can actually look at the RNA that encodes or is translated and makes that protein. They can take that out, just that one piece out, and then they can encase it in this lipid nanoparticle. And that lipid nanoparticle allows this mRNA, which is highly labile, to be stable. And as you know, these vaccines have to be kept at -70 to -20 degrees, depending on the vaccine, even with the lipid nanoparticle. So then what happens is when you inject this into the muscle, into the arm, it gets into the muscle cell, and then the muscle cell does what all cells in our body do. They start translating the RNA and they make proteins. They become protein factories, and they're very good at what they do, and they make the protein exactly the way coronavirus protein is made. And so this then gets taken up by professional, what are called antigen presenting cells, APCs. They get presented to T cells, they get presented to B cells. These B cells then eventually will make antibodies, and these antibodies then can bind to the spike protein and cause neutralize the virus. It's also important to remember that these vaccines can also induce T cell responses, which can actually kill infected cells, and they may actually prevent disease. So antibodies generally prevent infection, They also probably help with disease, but then T cells prevent disease. And so you get both of those things with these vaccines. So they tested these vaccines then, and this is just showing you the way they do these initial tests. They test for safety. So they looked at the low dose, which is 25 micrograms, the middle dose, 100 micrograms, and the higher dose, 250 micrograms. And what they looked at here was the ability to neutralize the virus. And that's shown here on the y-axis. This is showing the first dose at day 1 and the second dose at day 29. And I'll focus on this middle dose because this is what was carried forward to efficacy studies. You can see after 1 dose, you do get antibody responses, but after the second dose, it's much better. And what's amazing is the response after the second dose is actually better than what you see in people who've recovered from COVID. So this was very exciting, and this is one of the reasons that the government spent more money into sort of buying this vaccine after these results were made public. So the phase 3 study, the way you do these studies is you vaccinate a group of people, you give 15,000 people in this case the actual mRNA vaccine from Moderna. Another 15,000 got placebo, and neither the person who got vaccinated nor the person who is vaccinating knows who got what, nor the investigator. Only the pharmacist at the site knows who got which vaccine. You inject at 1, and then again 28 days later, you give the second injection. You look for tolerability during this time, safety, and then you rely on natural exposure. And then what you hope is that the people who got the mRNA vaccine have less symptomatic COVID. And the outcome was really just to ask, do people who develop COVID and they're PCR positive for COVID, are there less of those who get the mRNA vaccine? What I'll first talk about is the side effects, and these are the local side effects. And what you can see is that the majority of people have pain in the arm after the first and second dose, and this is much higher than what you see in placebo. And this is likely because you're developing a really good immune response to this. And anyway, up to 80+% develop this. Some people can get lymph nodes, some people can get swelling and redness as well. And you can also see that most of it is grade 1, which is minor symptoms. There are very few that are grade 3, which is severe. Systemic symptoms are those that are throughout the body, are also prevalent, and notice that they really come up after the second dose. Notice also that a lot of these symptoms are in the placebo group, so it's it is more than the placebo group for sure, especially after the second dose. And what you can see is headache and fatigue, myalgias or soreness in the muscle aches are the more common ones. But most people will get some sort of systemic side effect after the second vaccine. And again, that's to be expected, especially if you want sort of a good immune response. So this is the main part of the data, and this is the vaccine efficacy. So this shows you the number of people who developed symptomatic COVID infection. And in the gray line is the people who got the placebo. And in the blue line are the people who got vaccine. And what you can see, obviously, is that there's the vast majority of people who got a symptomatic COVID infection received the placebo injection. What's interesting as well is they gave 2 doses, but you can see even after the first dose, after 14 days of the first dose, you already start seeing a separation of these 2 lines. And you can actually statistically look at that, and you can see that even after 1 dose, at 14 days after the first dose, the vaccine was already over 90% effective. So the vaccine actually works after a single dose. However, you have to be careful. You likely need the second dose because that's going to maintain your protection level. It's hard to know how long that protection would last if you don't get that second dose. So I wanted to show you the next vaccine, which is the Janssen vaccine, which is the recombinant adenoviral vaccine. And this is potentially going to be have emergency use authorization by the FDA at the end of this month. UAB was particularly involved with this study. I'm a co-chair of this study for the North American sites. And what you see, this is the phase 1 data. And what you see is it's just a single dose. And this product can be stored at 2 to 6 degrees Celsius. So it can be refrigerated, not frozen. But what you see is that you don't get quite as good of neutralizing antibody responses compared to people who've recovered. But you do get a significant number of people who do get these antibody responses. And so the question was whether this single dose could work. And all I can give you now is a press release because it hasn't been published yet. And what you see then is 44,000 people were enrolled in this study in 3 different continents, in North America, in Africa, and in South America. I'm sorry, I deleted the wrong slide. So the vaccine was actually, I'll have to just tell you, the vaccine was effective, 72% effective in the United States, which, as you notice, that's a little bit less than what we saw with the Moderna and Pfizer vaccines. It was 66% effective in Latin America, and in South Africa, where we have these variant strains, it was 57% effective. However, what's perhaps more important is this is the first study that looked at severe disease as an outcome. And for severe disease, this vaccine was 85% protective against severe disease, even in countries where you have a virus that's a bit neutralization resistant or vaccine resistant. So these are I'm showing you here the COVID vaccine studies that are showing published efficacy to date, published or what's out in the press. And you can see Pfizer, Moderna, I talked about. AstraZeneca, I didn't talk about too much, but it's 60 to 90% effective depending on where it is. There was this thing about this low dose versus standard dose for this product. It turns out it's likely the dosing interval. So if you wait longer to give your second dose, it works better. Janssen, I talked about. Novavax is a protein-based vaccine. That's old technology. That study is currently being enrolled in the United States. However, they do have data from England and South Africa, again, in countries that have sort of the original strain and the what's called the B117, which is that first highly transmissible strain that's now in the United Kingdom. It worked against both of those strains. However, it didn't work so well against the B1351 strain, which is the one first seen in South Africa that seems to be somewhat vaccine resistant. It worked 50% for that. The Sputnik vaccine, interestingly enough, that was published in Lancet just recently. That's another recombinant vaccine. That's 2 different types of recombinant adenoviral vaccines. That showed 92% efficacy. Sinovac, which is another old technology, which is heat-killed vaccine, is interesting. It's shown widely varying efficacy rates of 50 to 78%, but they haven't published any of that yet. So just to end on vaccine allocation, Dr. Marrazzo talked a little bit about this, but this is where we are, where the healthcare personnel and long-term care facility residents were the first to be offered vaccine, and certainly at UAB, that's all sort of been done already. We're now working on frontline essential workers, persons over the age 75. As you know, we're now working on people who are 65 years and older, and we're getting to people with high risk medical conditions. And then the last one, obviously, is all remaining individuals. And as you know, more recently, it looks like we're going to have enough vaccine by the beginning of the summer to be able to vaccinate everybody in the United States that wants a vaccine. And possibly even before that, it's 600 million doses, which would be just about everyone. And as you know, unfortunately, not everybody wants the vaccine. So I just wanted to end on one thing that a lot of people ask: do I need to be vaccinated every year? And we do not know right now. I suspect we're going to be needing to be vaccinated more often than just this one time. And the reason for that depends on 2 things: viral variants and duration of immunity. So as we talked about this already, there's this B117 mutation that makes it highly transmissible. And then there's one that actually makes it more neutralization resistant. This study just came out last week in Nature Medicine, where the group at Pfizer actually looked at their vaccine and engineered these mutations to make this what's is the B1351, which is the one in South Africa that's vaccine resistant, partially vaccine resistant. And you can see these lines all go down compared to the wild type or the original strain, which shows that it is somewhat vaccine resistant, but the vaccine still does work in the test tube. And as I've mentioned, I think the best comparative data is the Novavax data, which shows you that it still works in South Africa, but 50% rather than 90%. And then this is the other data, which just shows you the longevity of the immune responses. And right now, the best we have is 4 months for the Moderna vaccine. This is the different age groups. And what you can see is you still have detectable antibody at 4 months out. It's going down, and how far it goes down, how fast it goes down, and whether that's the actual thing that protects you against disease and infection is unknown. But it is pretty good that it's still around for 4 months, and that's likely protective still during this time. So just to conclude, I won't harp on this, but this is why we've been able to develop the COVID vaccines in record time, beating the prior vaccine, which is mumps, by 4 years. It has to do with the knowledge we had, the new technology, the trial design, the rapid enrollment, the growing pandemic, and this relatively low mutation rate may now be changing, but it still is somewhat relatively low compared to some other viruses, especially HIV and Hep C virus. So like Dr. Erdmann said, I'd like to thank a lot of people, and I just put this up here, but this would not have been possible with all the people that are shown on this slide. And I appreciate your attention. Thank you.
Great, thank you all for the amazing presentations. We have several questions that have populated the Q&A box. And I think we have everybody turned on now. So welcome back, panelists. And I think I'm going to start with some questions going back to Dr. Marrazzo's talk in the beginning that specifically talk about some of the data that you showed on the cases in the United States in general. And someone was asking whether you could think about what the cause might be of the spike in the cases that started in November 2020 that we're still kind of in right now.
Mm-hmm. Yeah, that's a great question. Thanks, Peggy, and thanks, Paul and Nathan, for your excellent talks. So that spike in November probably reflects the cumulative effect of starting to get back together indoors, and particularly college students, university students, maybe high school students, but really college and university students starting to go back to school in late September. Every time you see a space or a time where people are engaging in more opportunities for transmitting the virus, it usually takes maybe 10 to 14 days, sometimes up to 3 weeks before we really start to see a spike in cases. And then, as I mentioned before, about 2 to 3 weeks after that's when you start to see the increase in hospitalizations and deaths. So that November increase probably was a cumulative effect of all of those things happening in the fall. And unfortunately, it was succeeded, or actually interposed, was Thanksgiving and then the end of the year, Christmas holidays, et cetera. And so we never really had a chance to recover from that surge that started in the fall, and everything just kind of built on everything else. So I think that's what ended up putting us in such a delicate situation in late December and early January.
Great, thank you. So another attendee asked, kind of more specifically narrowing down that data to a particular state, wondering why the per capita per day rates were so high in Alaska specifically, and whether this could be due to low resolution of the data in that state comparatively to other states.
So I think you're referring to the map that was the last 2 weeks, or the last week, I guess, in the New York Times. You know, case counts are so fraught with limitations in accuracy. And I'll give you a great example. And any of these things, I don't know the situation in Alaska. I have some hypotheses. I mean, Alaska is hugely sparsely populated, lots of physical distances. You can imagine that testing could be challenging to get out to a very large denominator of the population, particularly testing asymptomatic people. And you've got, you know, all kinds of issues getting specimens to a central laboratory in Fairbanks or Anchorage or Juneau or wherever you're talking about to get those things tested. In Alabama, if you look at our denominator of tests done every day, sometimes it was as low as just a couple thousand tests. And much of the time it was actually around 10,000 tests. So which would you believe as representative for generating the number of positive tests? You would believe the larger number. The other challenge is who gets tested. Remember that if you're testing people who are symptomatic, you're going to have a larger proportion of those tests come back positive, right? If you're doing widespread screening of people, you're going to have a lot, many more negative tests. So lots of things could be at play in Alaska. I suspect they have one of the highest vaccination coverage rates in the United States. And my suspicion, in fact, I think they've fully vaccinated at least 10% of their population. It's really incredible. They have a great public health system there, despite its rural nature. My suspicion is that probably with getting out there with intense vaccination efforts, they've had the opportunity to test more people, and you're seeing more detection that could be related just to aggressive public health interventions, but I'm speculating.
Yeah, so sticking kind of with the state-specific nature, what about Alabama? Do you think that Alabama in general is getting an unjustified bad rap, so to speak, for a slow distribution of the vaccine?
Well, if you look at the rankings, we are the anti-number one. I mean, we're almost last in the states. What is true and what is reported are two potentially separate things. If you talk to the Alabama Department of Public Health, who I have to say have been working 24 hours a day, 7 days a week, constantly, I mean, really, really trying to get a handle on this thing. Their position really is twofold. One, that they're not getting the vaccine that they need, and two, that the numbers administered are underreported because of sort of a lack of investment in our data infrastructure and our public health infrastructure. And there's no question, particularly as a state that does not have Medicaid expansion, right? We really have really problematic gaps in our public health infrastructure. So I honestly think it's probably a little bit of both. And the story probably won't be told for a while.
Great, thank you. So this question is kind of, maybe any of you can jump in to answer, but Jeanne, you might be in the best place to answer it given the stuff that you discussed, but this is about schools. Many people, I'm sure you've heard, suggest that it's not only best in general for children to be kept in school and schools to be open, but that it's safe for them and their families and the public to keep schools open right now. Do you think that this is accurate from the scientific perspective and the data that has come out, or reasonable? And if it's not, do you have an idea of when it might be reasonable to have schools open? That might be a loaded question.
It's not just a loaded question, it's a very long answer, which I do not want to embark too much on because I want to make sure that Paul and Nathan have plenty of time to talk. I will say, it depends. Not all schools are the same, right? You've got schools who have worked very hard to impose very good, strict measures for not just distancing, but cleanliness and good screening of kids who have symptoms and all that sort of stuff. And then you've got schools that have no resources and that are herding around 1,000 kids, right? Trying to keep things together. I have to say that I think that if schools were a gigantic problem, we would have seen more school-based outbreaks really taking people out. We haven't really seen that. I mean, there are teachers, of course, who've gotten COVID. So I think on balance, it's probably worth doing what we can to keep schools open with good support, good communication, and ultimately good ramp out of vaccine.
Thank you. Okay, so there are a ton of questions that came in about the vaccines. As you can all probably imagine that it's on everyone's mind, particularly if you're in line waiting to get vaccinated right now in Alabama. Several questions, so I'm going to kind of paraphrase. So if you asked a question about vaccines, I'm trying to kind of consolidate them into some single digestible questions. But a lot of people were really interested in reinfection. So reinfection post, already, being sick with SARS-CoV-2, but then also post vaccination. So Nathan or Paul, maybe one of you can jump in to talk about a little bit more about what we know from the science about reinfections and whether that's something that we should be worried about.
I can start with that, and then Paul can kind of jump in and talk about the vaccine side of things. So one of the things we know for sure is that reinfection is definitely a thing. It is not particularly predominant, at least early, but it does occur. And one of the things that we've understood from the very beginning is that coronavirus immunity is not particularly robust and or durable. And so that you take 100 people, get them infected, many of them will have kind of moderate responses. Some will have very, very poor immune responses. Some will have really strong responses. And then you play that out over time, and then it typically wanes over months to years. We have seen cases of clear reinfection in less than 60 days, although the kind of working guidelines are that it's extremely rare, less than 90 days, which is true, but then the frequency is going to go up from there. The amazing thing about vaccination, which Dr. Goepfert alluded to, is that when you short circuit the kind of the inflammatory immune dysregulation that happens with active infection, and you just give the immune system a taste of the viral protein, that the vaccination itself is extraordinarily effective. And that kind of just demonstrates what's the complexity of what's going on in the host and native infection, because there's so much noise in the system and you're just not able to make a durable response. We've had work that shows kind of persistent long-term inflammation that actually can even kind of crank up after resolution of symptoms. So there's a lot of noise that happens within the immune system that prevents good immune response. So the takeaway is that if you've been infected, you are, even ignoring the strain aspect of things, that there is an increasing risk over time for reinfection, which would always be an impediment for herd immunity. And then now as we mix in the strains, which have, depending upon which strain versus the prior immune response versus the current, there's either some or very little immune protection against reinfection, which the vaccine is better on all those fronts.
Great. Maybe Dr. Goepfert could jump in and kind of follow up on that to talk about whether or not or how, so say you were actively infected and recovered from SARS-CoV-2 and then you got a first dose of the vaccine. Do you need the second dose? I assume that would be, helping boost the immunity, but what are the thoughts on the second dose after kind of those two different types of exposures?
Yeah, that's a good question. The short answer is we don't know. I think the safest thing to do would be to give both doses even after an infection. As Dr. Erdmann mentioned, the coronaviruses in general make proteins and products that actually mess up your immune system. And so you don't respond as well when you're infected to the virus. And the vaccine only gives one part of it, and it doesn't give all those other parts that mess up your immune system. So you're going to get a better immune response. Now, you get infected and then you get a vaccine after that. It's likely you get a much better response than just the first dose of vaccine. However, whether it's as good as 2 doses of vaccine, I don't know. And I think the safest thing to do right now, unless you had really bad side effects, is to get both doses of vaccine. I should also say that just this week in the New England Journal, it was published on paper, if you will, the study by Oxford that showed that people who have prior infection are highly protected, at least for 4 months, against new infection. And there were only, I think, 2 people in healthcare workers who got reinfected within that time. However, if we know anything about coronaviruses from before, reinfection will happen, as Dr. Erdmann mentioned.
Great. So another question, kind of not related to vaccines, but related to SARS-CoV-2 in general, and maybe even coronaviruses in general, is that a question of whether or what is the mutation rate for the SARS-CoV-2 in respect to other viruses? Is the mutation rate higher? Does that have any play in how the immune system boosts a response, I guess, to the coronaviruses, and why it isn't as robust as some other viruses?
So, you know, it's fitting that we're talking about coronaviruses on Darwin Day, because it is evolving. And that is $1 million question, is how much is it evolving? We know it doesn't evolve as rapidly as viruses like hepatitis C virus or HIV. And fortunately, it doesn't evolve like that because we probably wouldn't be able to develop the vaccine so rapidly. However, we were hoping that it wouldn't evolve as much as influenza. And as you know, influenza evolves so much that we have to have a new vaccine every year. It looks, you know, this is a developing story, but I heard a talk from an evolutionary biologist last weekend who seems to suggest that what we're seeing now is mutation rates on par with influenza A, which would suggest then that we may need vaccines. I can't say that it's every year because influenza has a huge thing about going into different animals and coming out and things like that. I'm not sure if SARS-CoV-2 is going to go back in and out of animals, but nonetheless, we're likely going to have to be having new vaccines to combat this pathogen. And I will say that right now these rates of mutations are much higher because we're having such huge infection rates. If we can decrease these rates by masks, social distancing, and then more importantly, vaccination, we may be able to decrease the mutation rates and not have to vaccinate so often.
Great. So we keep hearing that we don't know yet. We don't know much. We don't yet know much vaccination, how much vaccinations will reduce the contagiousness of the vaccine. Sorry for my tongue twisting there. It would seem pretty easy to figure out whether or not vaccinations can affect the contagiousness of the virus, like through post-vaccination nasal swabs over time. Why do we not know more about this now? Do you guys have any thoughts about that?
I can start. So it's easy in theory, it's difficult in practice. So let's start, when we started these trials, you'd have to swab all 30,000 people every day and then do PCR testing on that. And remember, just in the very first part of that, we actually had a national shortage of nasal swabs. So we couldn't even do that at the time. And trying to get people to swab their noses every day and ship them is difficult. Now, having said all that, some of that has been done. AstraZeneca has done a little bit of that, and they do show that their vaccine, although I don't think this is published yet, there was another press release, does prevent 60 to 70% of asymptomatic of transmission. There's another study, and I don't know how, if we didn't want to do this study because of its logistical nature, where they were going to vaccinate college students and have them swab themselves every day during the study. And I'm not sure if Jeanne knows any more about that, whether that has taken part or not, but that is going to be very difficult to do. And I think that's why so far we don't have that data, but people are looking into that in the future.
There is animal, excuse me, animal model data which suggests that the if you inject them like a mouse through a tail vein and give them the injection through blood versus using the mucosa, that you don't make the same type of antibody, and so you can have some mucosal replication of virus, which is part of the consideration that even if you have good systemic immunity, that you may still be able to have sustain some modest degree of viral replication. I think we all expect there to be a reduction both in duration and intensity, but quantifying that precisely is more difficult.
And there is a company that is working with UAB called Ultimune preclinically, and then maybe clinically in the future, that is a mucosal vaccine that in animal models prevents transmission as well as protects against disease.
Nice. So there's another question about, so kind of moving a little bit away from vaccines. We'll come back. There were tons and tons of questions about vaccines and how they work. So given that receptor-mediated endocytosis is required for the viral entry and replication in cells specifically, might conventional therapeutics that affect the cytoskeleton, such as colchicine or cyclocalcins, be useful in treatment?
So I guess that would land under my purview. There's a bunch of different ways that we can target the virus. The trick is it needs to be specific enough. And then when you start thinking about viral therapeutics, there's lots of hurdles to overcome. One, it needs to target the specific pathogen. Two, it needs to be well enough tolerated, which is one of the reasons that we've been going so quickly to drugs that already have other purposes so we can repurpose them. Three is that there's a big difference between something that could change the viral life cycle in a culture when that's the only process, but then giving that drug, making sure it's bioavailable in the right places at the right time is another layer of complication. I mean, this was demonstrated pretty clear with hydroxychloroquine, which works in a culture system to shut down viral replication. But when you give it to humans, it has no benefit. And it was worth testing, and that's where kind of the hesitation to recommend it, but the push for studying it came from. I expect that we will continue to find more therapeutics. Some of them will be targeted specifically to COVID-19 and engineered for that. Others will be determined to have some activity. But until we really leverage human testing to determine how it can be used and how best to use it, we don't really have a place for it to recommend broadly. So this is happening as we speak with ivermectin, which has some preclinical data which suggests that there may be activity, but I wouldn't recommend it because we don't see how it performs yet in humans. And this scenario has played itself out dozens of times here over the past year. And it's why we're trying to test these in as quick and yet responsible and robust a way as possible.
I'll just add to that, Nathan. I just literally saw that Merck, the company that makes ivermectin, took the highly unusual step of releasing a press release that says specifically, do not use ivermectin to treat COVID-19. So it's kind of like even the manufacturers now are getting into the game to try to hopefully, prevent some of the misinformation that really took off with hydroxychloroquine.
Thank you for that. Moving back a little bit to vaccines and kind of the more specifics about how they work, a lot of people had questions about the muscle cells producing the spike proteins in terms of like how long after the injection does that start happening? And then whether or not other cells in the body will kind of pick up that duty as well and how long that might take.
So those are all really good questions. I think if you can get the mRNA in any cell, it'll make, because that's what cells do, it'll make the protein. But because you're injecting it in the arm, the vast majority of cells in the arm are actually muscle cells. Now there are other cells, there are other cells there that are likely doing it as well, but they're not a lot of them. So we think what's happening, this is mainly obviously done in animal models, not so much in humans, because you need to do a lot of biopsies to get this done, is that the muscle cells pick up the mRNA lipid nanoparticle. It stays in there, the mRNA, because remember, it's very labile. It dies off pretty quickly after that, after it gets taken up and then gets translated. And so it likely doesn't produce that for very long in most people, because not only does the mRNA not last for a long time, even inside the cell, but also the immune system will target that cell eventually and get rid of that cell that's producing it. And there's probably not a lot of cells that are making it, but the immune system is very efficient and it recognizes something foreign very quickly. And so yeah, any cell can make it if it takes it up. So if you were to give it in other parts of the body, it would probably take it up as well and produce the protein. But it just so happens that this is the easiest way. We've done this with vaccinations for a long, long time.
Great. So I feel like we've talked a lot about the specifics and intricacies of vaccines and how they work and how your cells are responding. But several folks have pointed out that there are, groups within the communities and populations who are scared and or hesitant or resistant to get vaccinated for fear of potential unknown long-term side effects. Nervous because the vaccine was, as we've talked about today, produced in such a short period of time. This is for any one of you, can you speak to, what you might say to people who are resistant, hesitant, or scared to be vaccinated?
Do you want me
We all have an opinion on that. You can go ahead, Paul. We'll jump in after.
I don't mean to take over. Well,
You're the expert. It's okay.
It depends on, you have to really ask them why they're hesitant to take the vaccine, because it can be very specific. Some people think that it was produced too quickly. And so, for instance, why don't we have a vaccine for HIV after 20 plus years of doing this, and now we get it in a year? And you have to sort of explain to them the differences, and it has to do with how these are totally different viruses. So it's easier to produce this. Some people are worried about side effects, and you have to talk about how many studies have been done already. And you have to acknowledge to them that, yes, you don't know all the possible rare side effects. I mean, these have only been tested in tens of thousands of people. And so common side effects we know about, and I showed you that slide. Very rare side effects we don't know about just yet, but they are going to be rare just because they didn't happen in these numbers of people. So one example is anaphylaxis. So anaphylactic responses that occur right after you get vaccinated has occurred in a number of people, possibly more than what we would have expected. And it turns out it may be the product one of the products of the lipid nanoparticle, but we're still looking into that. But that's still a rare event, and there's going to be other rare events. I mean, that's what happens with any product that you give to somebody. But again, you have to get into this risk-benefit situation. Now, the other thing, a lot of people say long-term side effects, and I don't know, there aren't really many long-term side effects from vaccines. There are rare side effects, but there's very few long-term side effects that they have this side effect for a very, very long time, that is with them for a long time. There are some immunological things, some nervous things that could happen, but those are extremely rare as well. Maybe Dr. Marrazzo and Erdmann want to take a stab at this as well, because it's an important topic. Oh, I'm sorry. One thing I will mention, especially in Alabama, is the Tuskegee experiment, and in other ways that people of color have been disenfranchised and used for unethical experiments. And it's very difficult to overcome that. And I don't know the answer to that. I know that the experiments that we do now are much different than they were then. We have consent processes that are formulated from members of the community, which none of that was available back then. But still, you have to gain the trust of a part of the community that you've totally abused previously. So that's going to be very difficult.
Yeah, I'll just jump in on that real quick and then turn it over to Nathan. I mean, I think, people talk about Tuskegee as it happened in the early 1900s, right, or the mid 1900s. The reality is that it's very much present with us because it's all about trust, right? And if you don't have trust in the healthcare system because you've had a bad experience, you haven't been able to access it, maybe your mother or your grandmother had a bad experience. I mean, you know, generations have long memories, right? So a lot of people who are grandparents have had some pretty bad experiences with the healthcare system here in Alabama and in general. So, you know, people appropriately have long memories, and it's not like just because I get up there and have pictures of myself getting the vaccine, they're going to erase those really profound, isolating, horrible associations. So I think all we can do is try to continue to build trust with these communities, you know, get more people who look like us, who look like all of us, and get out there and really try to be transparent about the facts.
I don't have a whole lot more to add other than to say, I mean, we're keeping plenty busy, but there's a reason we're here, and that's we want to make sure we're visible. It helps people when they see people that are either tied to institutions they know of or a familiar face. My patients know what I've been up to for the last year, and yet they still all ask me when I get in clinic, all right, doc, so tell me, do I need to get this thing? And they know the answer, but they still want to have an actual discussion about it. So, and obviously I embrace that, and that's important. There's a lot of chatter happening in all sorts of channels. The good news is that you look around, there's not a whole lot of medical authoritative figures that there's any dissonance. I mean, it's very consistent coming down, but I understand the questions, and it's all new, and this whole year has been an adventure. So, I mean, again, that's why we're trying to engage on it. But what social media makes seem like a pretty mixed picture. There's not that anywhere along those lines of kind of concern about it. So we're all very, very strong advocates.
Great. Thank you all so very much. We have come to the 1:32 hour actually. And I wanted to kind of close this out with one last question that is a little more lighthearted, but not so much. So the pandemic, you know, has led to lots of changes, right, for all of us, and how we work, how we live, you know, the things that we do. And many things, many people have COVID adopted puppies and kitties. And one question came in as to whether or not if you think that there's a chance that the virus could jump to these new adopted adorable family members that we have.
And it is a definite thing where it can happen in at least some circumstances. One of the challenging things about coronavirus long term is that it is there's such ubiquitous pathogens, and they bounce from different animal vectors from time to time. That is the presumption of how this all got started. And one of the unclear questions is, will that be a feature of mutation or infection changes going forward? That said, the number of cases that have been reported where it can actually get into animals that are clearly related to humans are pretty few. So that's not something I'm losing sleep over.
Yeah, I would say it's more important to love your pet. Don't worry about it.
There you go.
I would say it's more important how our pets are going to react when we have to actually go back to work like 10 hours a day. Probably not mine jumping into my lap. That's been the general attitude. So
Yes. Thank you all so much. This was a great way to spend our Darwin Day celebration, since we couldn't do it in person, and the topic is really relevant. And I know a lot of people joined in today to listen. And I just, you know, from the Darwin Day Committee, from UAB Department of Biology, and the College of Arts and Sciences, we thank Dr. Goepfert, Dr. Marrazzo, and Dr. Erdmann for spending their time with us today and giving us some great information about how UAB is and continues to fight the COVID-19 pandemic. Thank you all for joining us today, and thank you for the hard work that everyone at UAB is doing.
Thank
thanks.
you.
Stay safe, everybody.
Thank you.